Okay, so we've talked about 3 different methods of which you can solve systems of equations. The first one being by graphing, the second one being by substitution, and the third one being by elimination. All 3 we're going to practice today, and then as we go through systems of equations later on in this unit, you just have to figure out which one is your strength, which one you prefer the most, and honestly depends on the type of equations you're given. So let's go over the 3 methods. The first method is solving by graphing, which we spent a couple of days on, or several days really. Okay, the idea of solving by graphing is that you're going to solve each equation into slope-intercept form, and the graphing is really valuable if the y-intercept is a nice integer. If you end up getting a fraction as an integer, then the graphing is kind of out the window. So that's why we learned the other 2 methods. So if we look at number 1, I'm going to solve for y on both the equations. The first equation, I'm just going to subtract x, so y equals negative x plus 3. Nice and easy, right? The second equation, I'm going to subtract 3x first, so I have 2y equals negative 3x plus 14, where then I would divide by 2. So y equals negative 3 halves x plus 7. And then I'm going to graph both equations and see where the lines would intersect. The first equation was y-intercept of positive 3. So then I would graph my y-intercept first. And then my slope tells me which direction to plot my next point. So since it's negative 1, we're going to make it a fraction by putting it over positive 1, which means I'm going to graph down 1, right 1 from the y-intercept of 3. Down 1, right 1, 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 and then up 1, left 1 in the opposite direction, up 1, left 1, up 1, left 1, where then I would just connect my dots by drawing my line using a ruler or a straight edge. The second equation has a y-intercept of 7, so we start at positive 7 on the y-axis. Since my slope is negative 3 over positive 2, that means I'm going to go down 3, right 2 from that y-intercept of 7. Down 3, right 2, down 3, right 2, down 3, right 2, down 3, right 2. And the point of intersection where the 2 lines meet is this right here. Again, I like to circle it just so I can be able to tell where they intersect visually. So that coordinate or ordered pair would be 8, negative 5. And there's my solution. Let's try another one where we're graphing, number 2. Graphing is especially handy. I mean, not that you can't do it any other time, but it's especially handy whenever one of your equations is x equals 4. But let's go over it. So number 2. I'm going to solve for y by subtracting x first, so 2y equals negative x plus 6. Then I'm going to divide by 2, when I simplify, I have negative 1 half x plus 3. My y-intercept on the first equation is positive 3. My slope is negative 1 half, which means I'm going to go down 1, right 2, 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 and then up 1, left 2, up 1, left 2, up 1, left 2, up 1, left 2, up 1, left 2. Okay, the second equation is x equals 4. That means it's going to cross the x-axis at positive 4 and be a vertical line because it has an undefined slope. And the point of intersection is this point right here, and that point is 4, 1. Okay, so after graphing, we learned how to do solving by substitution. This is especially helpful when one of the equations is solved for a specific variable and the other is not. Now, this is also useful whenever, if I were to solve for y equals mx plus b on the second equation, the y-intercept wouldn't work so well, so graphing is kind of out of the question. So here's what we do. When one of the equations is solved for y equals mx plus b, or just whatever variable it is, to be honest, we're going to take that expression, so 7x plus 6, we're going to substitute in for the y in the second equation. So we're going to rewrite it. 4x minus 3 times 7x plus 6 equals 16. And then I distribute and solve like we would solving regular equations. So 4x, negative 3 times 7x is negative 21x. Negative 3 times 6 is negative 18. Equals 16. 4x minus 21, x is negative 17x, minus 18 equals 16, where I would add 18 to both sides. So 16 plus 18 is 34 equals negative 17x. And then I would divide by negative 17. So x equals negative 2. Then I would take that x equals negative 2, substitute it back into one of the original equations. It doesn't matter which one. I prefer, honestly, to do it to the one that's already set equal to a variable, so the first one, because it's a little easier to do the math there. 7 times negative 2 is negative 14. Negative 14 plus 6 is negative 8. So y equals negative 8. So I have my x, I have my y. So my ordered pair is negative 2, negative 8. If I look at number 4, same thing. Since one of them is set equal to one of the variables, all I'm going to do is substitute the negative 5 in for the y for the second equation. So I'm going to rewrite it. 8x plus 5 times negative 5 equals negative 17. So I have 8x minus 25 equals negative 17, where I'm going to add 25 to both sides. So 8x equals negative 17 plus 25 is positive 8, where I'm going to divide by 8. So x equals positive 1. Then I'm going to take that one and substitute it back. This time I have no choice. I have to substitute it into the second equation because there is no x value in the first equation. So when I substitute the 1 in for x, it's 8 times 1 plus 5y equals negative 17. 8 times 1 is 8 plus 5y equals negative 17. I'm going to subtract 8, so I have 5y equals negative 25. Then I'm going to divide by 5, so y equals negative 5. So I have my x, I have my y. My ordered pair would be 1, negative 5. The second, or number 5, this one is set equal to y as well. So I'm going to take negative 2x and substitute it into the y for the second equation. So 7x minus 8 parentheses negative 2x equals negative 23. So 7x, negative 8 times negative 2x is plus 16x equals negative 23. 16 plus 7 is 23x equals negative 23, where I would divide by 23, and negative 23 divided by 23 is negative 1. Then I would take that negative 1 and substitute it back into the one of the equations, the first one being the easiest. If I do negative 2 times negative 1, that's positive 2. So y equals 2. So my ordered pair for that one would be negative 1, 2. The second, or the last one on substitution, number 6, is set equal to x. So I'm going to take 2y plus 1 and substitute it in for x on the second equation and rewrite it. 3 times 2y plus 1 minus 6y equals 3. Distribute and solve. So 3 times 2y is 6y plus 3 times 1 is 3 minus 6y equals 3. Here, 6y minus 6y is cancels, so I have 3 equals 3. Since 3 does equal 3, that's a true statement. That means this is a special case where I'm going to have all reals or infinite solutions, whichever one is applicable. Then we go into elimination. The elimination comes in handy whenever my equations are in standard form. Okay, so that is whenever you have to multiply or change the signs of one of the equations in order to cancel. But more often than not, you're going to see somewhere you have to multiply by an integer. So if I look at number 9, I definitely have some options. I can cancel my x's by multiplying the second equation by negative 3, or I can cancel my y's by also multiplying by negative 3. So this one's one of those special cases. Let's go over it. So either way, I have to multiply the second equation by negative 3 in order to cancel the variable. So negative 3x, negative 3 times 2y is negative 6y, and negative 3 times 11 is negative 33. So what happens here when I now cancel, if I add my equations, 3x plus negative 3x cancels. 6y plus negative 6y also cancels, so I have 0 on my left side. 27 plus negative 33 is negative 5. So earlier we saw where 3 equals 3, that means my equations are equal or exactly the same, so it's infinite solutions. Whereas this one, since 0 does not equal negative 5, that means this is that special case where my lines would be parallel. And that means no solution because they would not intersect. Now, number 10, I have some options. This one definitely is the longer way to go because I have no other option. So if I look at canceling my x's, my least common multiple for 4 and 7 is 28. That being said, I would multiply the first equation by 7, the second equation by 4. My other option is to cancel my y's, where my least common multiple would be 15. So I would have to multiply the first equation by 3, the second equation by 5. Either way, I have multiple steps here. So it just comes down to preference. I'm going to go ahead and cancel the y's. So I'm going to multiply my y's, my first equation by 3 and my second equation by 5 to make them 15y's. So 3 times 4x is 12x. 3 times 5y is plus 15y equals 3 times 22, which is 66. 5 times 7x is 35x. 5 times negative 3y is negative 15y. And 5 times negative 32 is negative 160. Now, I can cancel my y's because I have positive 15 and negative 15y. So 12x plus 35x is 47x. My y's would cancel, equals 66 minus 160, which would be negative 94. Then I would divide by 47, and x equals negative 94 divided by 47 is negative 2. So my x is negative 2, where now I'm going to take that and substitute it back into one of the originals. It does not matter which one. If I do the first one, it would be 4 times negative 2 plus 5 times y equals 22. 4 times negative 2 is negative 8 plus 5y equals 22. I'm going to add 8 to both sides, so 5y equals 30. Divide by 5, so y equals 6. Where my x value is negative 2, my y is 6. My ordered pair is negative 2, 6.